Hello everyone and welcome back to the channel. Have you ever wondered how you can jump on a video call, share your screen, or even stream live directly from your web browser, often without needing to install any plugins? This magic is powered by WebRTC, or Web Real-Time Communication. In system design interviews, understanding web real-time communication is crucial if your system involves any form of direct real-time audio, video, or data exchange between browsers or devices. Today, we are diving into what WebRTC is, how it works, and its unique place in system design. Okay. Traditional web communication built on HTTP and even WebSockets. It's a fantastic way and it's fantastic also for many things. But for truly real-time audio and video, they often fall short. HTTP is a request response protocol, too slow for live streams. WebSockets provide a fully duplex communication, but if all audio and video streams for a call went through a central server, it would introduce significant latency, consume massive server bandwidth, and quickly becomes a major bottleneck. For a seamless, low latency video call experience, we need something more direct. We need a true peer-to-peer communication. So that's where WebRTC shines. It's an open source project that enables real-time communication capabilities directly within web browsers and mobile applications. It's not just a single protocol, but a collection of standardized API and protocols that allow browsers and devices to establish direct peer-to-peer communication for transmitting audio, video, and even generic data via data channels. The key differentiator is that after an initial setup, the actual audio and video data flows directly between the participating devices, bypassing your central servers for the media stream. Think of it like making a direct phone call between two browsers without your server acting as a continuous relay. Okay, so we need to understand how it works, and I would just say, if you don't understand this part, I highly recommend you to just repeatedly see it again and again and again, because it's not that easy. So, the crucial point that often trips people up, WebRTC is not completely serverless, while the media streams itself is peer-to-peer. You still need servers for initial handshakes process called signals. Okay, the process happens in 3 steps. So let's say that we have a peer, and we have another peer here, and we have the server here. First, everyone will single the server, which is the matchmaker. Before two peers or two browsers can talk directly, they need to exchange metadata about themselves, like their network addresses, session description, what audio video codes they support, and how to traverse network obstacles. This exchange happens via a separate signaling server. The server is not a part of the WebRTC itself. You build it using technologies like WebSockets, HTTP, or any custom messaging solution. It acts as the matchmaker, helping two peers find each other. So these two peers will find each other with the help of our servers. There are 2 things we need to talk about, which is SDP, which is Session Description Protocol. This is exchanged during signaling to describe media capabilities. And also we have ICE candidates. These are discovered network addresses like local IP, public IP, and port communication that a peer can use to communicate. and also we need to, yeah. So the next step, we have the net traverser, sorry. So once peers have each other addresses, like they will exchange their addresses in the server, and right now they will have each other addresses. They try to establish a direct connection. So once they have each other addresses, like P1 have the address of P2 and P2 have the address of P1, they will try to establish a direct connection. But the internet is quite complex, and most devices are behind NATs, which is Network Address Translator, and firewalls. WebRTC uses specialized servers to overcome this. And this has happened by two things. There is STUN, which is Session Traverser utilized for NAT. These are lightweight servers that help a peer discover its public IP address if it's behind NAT. This is often allows direct P2P connection to be made. And also there is TURN, which is traversal using relies around NAT. This one, if the first one, which is a stun, fails, the TURN or the turn acts as a relay. All media traffic for that specific connection flows through the turn server. This adds latency and cost, but ensure connectivity as last resort. And after all of that, the peer happens and the peer connection happens. After the signaling and the NAT traverser are complete, WebRTC establishes a direct peer-to-peer connection for the actual audio, video, and data transmission using protocols like RTP and SRTP, which is a real-time transporter protocol, and secure RTP for encryption. This is where the magic of low latency direct communication happens. Okay, why WebRTC matters in system design? WebRTC offers a lot of power benefits for system design, but also introduces and introduces some sort of limitation or consideration. First, we have latency. It's direct B2B data flow. It's ideal for real-time media data, so it provides us a lot of low latency. Okay. The consideration, we'll talk about it in the next slide. Sorry, I just made a problem. Right now, we talk about all the benefits. The next slide will be the considerations. Number two, we have reduced server cost and load for P2B. For one-on-one calls, if STUN succeeded, your central servers are largely free from media relying, saving bandwidth and CPU. Number three, browser native. No plugins are needed, making it easy for users. And four, scalability for one-on-one media. The P2P nature means scaling bandwidth is offloaded to the client themselves. Okay. But we have some challenges. The first one, we have the signaling server scalability. Your signaling server still needs to scale to handle all initial connection requests. Number two, the turn server cost. If significant portion of your users require turn relies, it can become very expensive as turn servers consumes considerably bandwidth and CPUs. Number three, complex network environment. Dealing with various NATs and firewalls can be tricky to debug. Number four, group calling complexity. For group video calls and participating a purely P2P mesh approach where each client receives in one streams becomes bandwidth intensive for clients. For larger groups, you will need specialized architecture like SFU, which is selective forwarding unit, and MCU, I guess multiple control unit, but this is beyond the scope of this video, so we'll not talk about them that much. You just need to know that group calling is not that easy. It's pretty complex. And that's it. So how we will talk about it in the interview. So in an interview, bring up WebRTC when a core requirements involve. First, we have a video conferencing, like Google Meet, Jitsi Meet, something like that. Number 2, live streaming, especially low latency interactive streams. Number 3, peer-to-peer file sharing in browser. Number 4, voice chat in online gaming. Lastly, any browser-to-browser or mobile-to-mobile real-time data exchange. Always highlight B2B nature for media, but crucially emphasize the need for signaling, stun, and turn servers, and discuss the scalability application for group calls. And I guess I need to make videos about stun and turn videos, but I guess you will never face them in assistance interview. I don't know. So yeah, that's it for this video, and see you in the future.